Welcome to another exciting computer architecture class. I thought I would take a few moments to do a little bit of lecture before we dove into a review of the homework. Homework assignments, let's just make sure we are on the same page here. We've got a homework 7, which is due on the 22nd, end of day, which is end of day on Thursday. It covers little information about threading and networking, and it is titled Network Programming. So what I thought I would do is give you a little bit of background on the network programming and the threading, just so that you can have that in your toolbox when you encounter it. Let's hit on, well, maybe let's do this. We'll do the threading first, and then we'll do the network programming. I think that's better. So we'll start with threads, and then we'll go to network programming, and then we'll cover the rest of this homework so that you guys can be prepared for it. And then you've got a midterm due the week following, and that'll be a Thursday. So we'll cover that too. But I just wanted to go through and do a little background coverage on the threading and the network programming, just so that I could know that you guys have seen it before and it's not all new material. So without further ado, let's just discuss a little bit about threading. And it is a mechanism of concurrency. We already covered the idea of multi-threading versus multitasking. Multitasking has protected memory. True concurrency means we can do two things at exactly the same time. We get that with multi-core systems or with networks of workstations. And we had the Flynn classification, the Flynn taxonomy, which enabled us to identify SysD, SIMD, MISD, and MIMD. And by now you guys are well familiar with that stuff. So single instruction, single data, that's your standard von Neumann style computer. And then there's the MIMD, multiple instruction, multiple data, and SIMD, which are truly parallel computers. And you would see SIMD architectures for things like vector-oriented machines. And that's common. So this would be the so-called SSE instruction set, MMX instruction set, AltiVec instruction set. All of these things which process a vector, that is an array of data, and typically the array is homogeneous. That means it's all the same data type, single precision floats or integers, something like this. Normally we'd like to see 10 CPUs give us a 10x speed up. But typically we get a speed up that's somewhat less than 10. And we know that is at least in part because of Amdahl's law, or rule of thumb, if you like. And when it comes to multi-threading in Java, it's typically software-based threading. That is called temporal multi-threading. We do a kind of task switching with a low overhead context switch because we're sharing threads. But then there's this other thing that Intel has come out with called, well, this is more trademark in marketing than anything else. They call it hyper-threading. Hyper-threading. You know, so, oh, what's that? Well, that's not software threading. That hyper-threading, that's threading inside the CPU itself. And it is simultaneous multi-threading, and it can represent a form of true concurrency. It is hardware threading. And they have this in all the modern processors. AMD has it too. They don't call it hyper-threading because they don't want to infringe on the trademark that Intel has. But it's the same thing. So when we have the so-called multi-threaded systems, we expect that within a software temporal threading system, we would be able to switch between one thread and another using a round-robin scheduler. And typically we would assign a priority to each one of the threads, and that priority would give them some favor. And you would get hundreds or maybe thousands of cycles spent on each thread before you go to the next thread, and all the threads that are in waiting have to just stop and wait. They don't make any progress during that process. So that's a software thread. We share memory, and we do that sharing of memory using a task. And that one task exists in a so-called multitasking operating system where each task has its own protected memory. So if we have to have multiple threads, like thousands of threads, we have to be sure that they are good neighbors with respect to one another. But if we're the programmer, that's our responsibility. That's our job. And, inside of an operating system, multitasking operating system, like the one that you're viewing now, this Mac, for example, the operating system has a task. And at the operating system level, it also has a scheduler. And that scheduler also has associated priorities with each task. And each one of the tasks has protected memory. And if one job dies, presumably the other jobs can continue and the whole system doesn't have to be rebooted. And so the task scheduler, yep, you got a question?
Yeah, I just had a question about the hyperthreading, the AMD and Intel. So it's basically the same thing. It just one is the copyrighted name. So is there some kind of protocol? So say if a software wants to utilize some of the threading that the hardware for the hardware threading, how can a software, without knowing if the person's on an AMD or an Intel processor, know how to utilize that threading process? Is there like some kind of universal protocol for software to access it, or do they have like different versions for both?
That's an excellent question. And the answer is it depends. And that's not a really great answer, I know. If you're a Java programmer and you're using standard Java APIs that I'm aware of, you don't get that level of hardware access. If you want that level of hardware access, you can do it through native method invocations. And so there are two ways to do that within Java. One is a Java native invocation, JNI, and the other is Java native architecture, which is the more modern one. In terms of going from one operating system to another with a standard API, while Java doesn't give it to you, Unix might. And in the portable operating system for Unix, they give you a special layer, a substrate known as POSIX. And in the POSIX system, you can get portability in C++ systems programming languages. You can do that. However, having said that, when I did this once, we ended up with having to take heroic circumstances, heroic efforts. So not to put too fine a point on it, if you look at one of my papers on vector programming, here's optimizing superscalar vector architectures. When you look at that paper and you're trying to get deep into the code so that you can vectorize Java by using vectorizable C code and the Java native interfaces, you basically go straight into the hardware, right? This is the part where you're kind of asking, how do I know what kind of hardware do I have, right? Does Java have access to this vector unit? The answer is yes and no. Through native method invocations, that is C subroutine libraries, yeah, you can do it. But once you do that, you cease to have what's known as portable code, right? Now you became really tied to, in this case, the G4, which is a PowerPC architecture. You tie your code to that, and then you decide, oh, I want to go to Intel. You're screwed. I mean, no kidding. You just can't do it. They don't give you a portable operating system software interface library for things like SIMD style programming or MMX instructions because that's Intel proprietary stuff. And if you're on a G4, you're using the AltiVec vector processing unit. Once you open the hardware book and the operating system book to gain access to the high speed stuff, all the bets are off. And you can kind of see what's going on because you're going deep into assembler language code and you're trying to manipulate things down at that level. So here I am taking a for loop and building in a four index stride. taking that, building up an array, and then passing it into um, a vector invocation. So you're unwinding for loops. You're doing all this really wacky stuff. Here I am going 8 at a time, trying to vectorize things. And now I'm doing an invocation, summing using AltiVec, which is the vector processing unit. And I have to do things like vsplat and all these invocations. And I'm calling in pointers and I'm doing all kinds of crap that you wouldn't have to do if you were a normal um, Java programmer. So when you look at something like this, that's the C code, right? That's actually going in and using, vector addition in order to get some additional throughput. And then you have to invoke that from within a Java program, which means you've got your own little overhead for communicating and for unwinding loops in order to gain access to the high speed stuff. And if you want to build, a relatively high level accelerated Java advanced imaging library like we were doing, you can do that. And you can put in things like convolution and maybe higher level stuff than just simple addition. And then you can call it a big win, right? A win in the sense that it will be effectively faster. So there was a scientific application library. I used to teach this, Mercury computing. And what that would do is it would do like an FFT down at the hardware level much, much faster than you could do, let's say, in a Java program, because it took advantage directly of the hardware, totally non-portable. And so the answer is yes, it's possible. The efforts you put to doing it can be heroic. Once you start experimenting with this, the amount of energy that you spend doing this kind of programming is unbound. I mean, you're looking at stuff here like this, and you're looking at the assembler output after the Java compiler is done, and you're looking to see if you are doing an invocation of low-level native methods. So vectorizing, you can do it. You can do hyper threading inside of a Java program. You can do it. It isn't pretty. I mean, just look at what you need to do a square root. I mean, this is if you don't have a library versus you have a native library versus you have an AltiVec library, you're just doing a big dispatch based on what kind of hardware is available. Nasty stuff. So yeah, it's possible.
And there's no public organizations that coming from a programming background, it seems like there's a lot of public organizations that create these like protocols or just general abstract systems that you don't have to tie to any one piece of hardware system. There's nothing like that for hardware, where if I want to create, a new Java interpreter like you're talking about before, I have to then tie it to some certain hardware processor. Like there's no public.
Yeah, here it is. POSIX threads. This is the portable mechanism for doing hyper threading. And yeah, there's an organization, it's the IEEE, and yes, they have a standard. And sure, you can find it in these different operating systems, and you're going to take a little bit of a speed hit. It's portability versus speed. But if you decide that's something you want to do, you can find some packages that'll do it. Now, if you try and invoke these C programming features from within Java, you may have a problem. But if you use a Java virtual machine that's already been written to take advantage of these things, then you have a hardware threaded approach to accelerating the Java virtual machine. So you're really getting, what you really want is you want the virtual machine authors to be hyper threading savvy. That would be the people you would really want to have approach this, because then you'd have all the Java programs accelerated when they start doing multi-threading, because the multi-threading would be in hardware. But the way things are, typically we don't know what's going to happen when we encounter a thread. Maybe we'll have green threads, maybe we won't. And that's just the way it is with the Java virtual machine. So, and I'm not even sure if they would tell you that when you just do the mixed mode hotspot. Yeah, this guy, the hotspot thing, that's like a trademark. And this is a really old version of the virtual machine in here. That's like a Sun-based version, not even an Oracle-based version. So that's a good question, and I don't have a good answer for you, or at least not a satisfactory one. POSIX can do it, and if you're a C programmer, that's the way to go. And it seems to be available on all the popular operating systems. So
Okay, thank you.
yeah, maybe that answers your need. Not sure what would happen if you were a C# programmer or Python even. Oh my gosh. So your task scheduler, that's typically a software program that runs in the operating system, not inside of the CPU. Whereas the hyperthreading, that can actually run in the CPU. So your software thread runs without the protected memory. It has the low overhead context switch. The symmetric multi-threading, SMT, goes by the name of hyperthreading. That's the Intel trademark. And it is in comparison to instruction level processing, which we saw from the superscalar machines, it gives you a so-called thread level parallelism, true concurrency inside of the core, inside of each one of the cores in the CPU. So a multi-core CPU, one core could have two threads, and they're sharing resources, and they can have conflict, which is why you don't have too many more than two threads per core. And so that's kind of like my little overview of threading. When you have threads, you can have a pipeline, a multi-threaded pipeline. Typically, you would do something like this. You'd say something like ls, pipe it into more, or ls, pipe it into a grep on, look for my name, and then pipe into a grep on, look for my first name, and then pipe it into another grep, or pipe it into a sort, or pipe it into a more, right? Each one of these pipes could run on a separate core. And in principle, they can pass data from one place to the other and work like an assembly line. And you've seen this too in like, you could say ls, pipe it into more. I spell it right. And that's, typical. Ls, pipe it into sort, pipe it into more, or pipe it into, I don't know, grep on zip, and then pipe it into more. Now only the things with zip in it show up. So that's how the Unix tools work with piping. And if you're in a symmetric multi-threaded environment, you can have these things dispatched to multiple cores. So that's a way in which you can do true concurrency. There's an element here which is showing you the task, and there are multiple threads in each one of the tasks. And in an environment where you can create threads with wild abandon, you can have thousands, if not tens of thousands of threads. Like, for example, a Java virtual machine. And that brings us to this nice idea about memory swapping. And that's when the memory for a task has been protected and has to be swapped out of, let's say, the disk space before it can be executed. It comes out of the disk space, goes into RAM, and then goes back to disk space once there's some execution taking place. That's called the context switch. And thrashing happens when no progress is made because you spent so much time swapping the memory from the disk into RAM that you didn't have much time to spend on the thread itself. And so then you just swap it back out. And if you had a little LED showing you when the disk was being accessed, it would just be sitting there blinking, and you could even hear it if it was a mechanical drive going tick, 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 thrashing, trying to make progress, but not actually going anywhere. So threads don't thrash because they share memory, and they give that low overhead context switch. And this is particularly true for the software threads. Hardware threads also don't thrash. And so one task can have many threads, and deadlock occurs when two threads contend for a resource and they can't get access to it. So if I lock a file and another thread wants to use the file, if my thread dies while the file lock is in place, nobody can make progress until somebody breaks the deadlock, perhaps a supervisor. And so here's a threaded pipeline. And this is just like the pipeline that I just showed you, only here we're seeing the connection, the vertical bar connection being done with these little gray arrows. So we have built-in multi-threading with Java. We have mechanisms to lock resources called synchronization or synchronized, which is a Java keyword. And we have schedulers inside of Java. And the schedulers allow us to group threads together, assign priorities, and kill entire groups at once if we like. And this is how you make a thread. You pass in something that implements the interface runnable, or you subclass the thread class. And I think you've seen me do this already. So here's something that has a run method called the interface runnable. And if I implement that interface, my class must be declared as abstract, or it must provide an implementation for the run body. That is to say, oops, where did it go? Yeah, that is to say this part right in here, if you want to implement it, you have to provide a run method. It doesn't have to do anything, but it has to be there, or else class foo would have to be abstract. Once it's implementing runnable, I can pass it to the constructor of a thread, because threads take runnable instances as part of their construction. And then when I do a t.start, here's t as an instance of the thread, t.start makes it ready to run. PowerPoint has a nasty habit of automatic capitalization, and I don't know how to turn it off. Oh, there it is. So yeah, it did the same thing over here. Darn it. You have this class. That's not supposed to be capitalized. So runnable, that's the constructor's argument for the thread. It gives you a callback. That's an inversion of control pattern. So the scheduler knows how to run the jobs, and jobs know how to run themselves. So it just invokes the run method. So schedulers don't know what is inside of the run method implementation. All they do is invoke run. And so here's the life cycle of a thread. Threads are born when you say new thread. Then they start, and that makes them ready to run, but they're not running. Then the thread scheduler invokes the run method, and they become running. And then they get blocked either because they sleep or they have to wait for some kind of additional input. Perhaps they're sucking on a socket, and the socket's gone dry in terms of its stream. And then they become notified by the scheduler, and they start to become ready to run again. And then they start running until the run method returns, in which case they're dead and harvested by the garbage collector. And returned, their space is returned to the heap. And so here's another way to look at it. Things that will stop a thread. You can invoke the sleep method, the suspend method, or have it blocked. Something is not able to do I/O, and it becomes non-runnable. And then when data becomes available, they get notification, or they get an invocation of resume. They're unblocked, and then they can become runnable again. And then the scheduler will wake up and say, hey, you can start to run. And so the finalizer is invoked to reclaim the space, put it into the heap, which is really just a data structure that has a pointer to areas in memory that are available for creating new data elements. So every time you do a malloc in C or make a new instance in Java, you're basically allocating data off of the heap. If you do that without regard for anything during runtime, it creates what's called a memory leak, and that'll eventually kill your program because you'll run out of memory. And let's see now. Here's an example of some threading. I've got subclassing of the thread, implementation rather of the run. And then I make a new instance of this class and this thread, and then I call t.start. So you don't need to implement runnable if you're going to subclass thread. That's implicit. Whereas here you're implementing runnable, you've got the run method. Now that instance can be passed into thread constructor. So here is an anonymous inner class called new runnable with a run method that does nothing apparently. And then you can call t.start, and that will probably launch and finish immediately, or very quickly anyway. And here's a little thread demo, which has a sleep instance in it, does some printing, and looks like it's got a printout that's going off the page here. And then there's this thing called the daemon. And that's a kind of thread that dies when the main method dies, but you can make a non-daemon version of the thread that will continue to allow the Java virtual machine to live on even after your main method dies. And that's kind of interesting because you might like that. I mean, you might want to say, look, I don't need the main method anymore, but I want this thread to keep running. And then we get into the complex notions of thread safe, deadlocks, and synchronized. And I think that's about all the thread stuff I want to do right now. So that gives you a little bit more insight into threading. We've kind of alluded to that before, but I wanted to just run you through the formal presentation. Let me just see if there's anything else in here that I need to cover. I think, yeah, that's about it. And then the other thing I wanted to do was a little bit of a review for network programming. This is one of those things where you kind of have to get a little bit of a background to kind of get through this homework. So we talked a little bit about the ISO OSI model. There's an international standards organization called ISO. The OSI model is the Open Systems Interconnection model. And that's the model that has substrates, 7 layers. And that's what we alluded to before. And the layers help you to identify where the services are for various kinds of, I'll call them killer apps like Telnet and mail and printing and FTP, which is file transfer protocol. All these different sort of things we expect as services from the network. And we can find that list of services in Etsy services, and each one of the services has a port, and there's 14,000 of them on my Mac. They're not all active. And when you're trying to do computing on a network, you need to know about the services. And when you do network programming, which is a form of network computing, you're going to end up writing your own services. So you'll be using ports that are not already occupied by the Etsy services list, or else it creates a conflict. With cluster computing, you get a whole bunch of computers that are just like one another, typically geographically co-located, like a bunch of computers in a room. And then you try to use a master-slave paradigm for dispatching work to each one of the computers in your little cluster. You will probably find that it's not easy to balance the load so that they're all busy all the time. You probably need benchmarking in order to see how much acceleration you get. You need a mechanism to know when computers are available, so volunteer computing is important. And then you can proceed to detect when computers are idle so that you can dispatch additional work for each machine. And so here comes the gold problem for computer science and software engineering for that matter. How do I partition a problem so that it can work on a cluster or any parallel computer for that matter? That's not easy. And so I use Java Web Start for deployment, but that's been thoroughly deprecated, and I'm not sure what to use next. File systems are distributed. That's typical. Beowulf lets you do clusters. Typically, computer clusters, you have centralized management, and that means you have a single point of failure, but at least you have a way to orchestrate what's going on with all of the little worker nodes. And with grid computing, you have non-similar computers known as heterogeneous computing. And they don't have to be geographically co-located. They can be all over the place. And for examples on that, you can see SETI, the search for extraterrestrial life, BOINC, Globus. There's some pharmaceutical companies that use these volunteer computing systems in order to search for new drugs. I suppose you could use it to search for COVID viruses or something. And then comes cloud computing. And this has been made famous by Amazon. So when you think about cloud computing, I think about AWS. Oracle has cloud computing. I think Google has cloud computing. I think IBM has finally decided it wants to do cloud computing. What is it with those guys? I mean, really? Now you finally decided? And this is like 10 years after Amazon has been launched with AWS. So they gave Amazon a 10-year runway. IBM, hey, they used to be innovative, but now I don't know what they do. So what does Amazon do for you as a cloud computing system? Well, it can give you basically a machine that you can run that isn't yours. That's what an elastic computing system is. It's a Unix system that they run, but you administer remotely. And they give you a whole bunch of services that you can use for storing files and doing domain name service lookups. They have something called Lambda, which will do computations, all these different interesting and wonderful things. And they've got charging down to a science. So if it was their own business unit, I think it would be like a top 50 company if it was a separate company. So here's the 7 layers of networking: the physical layer, data link layer, network layer, transport layer, session layer, presentation layer, and application layer. Physical layer, that's your bits, typically transmitted through energy means of propagation, such as fiber optics propagating light, or RF propagating some sort of Bluetooth or Wi-Fi, or I don't know, any kind of infrared transmission. Any energy can transmit bits. Then you have data link protocol data units, the LPDU, which are also known as frames, or sometimes called packets. And if you have point-to-point protocol, you would have a link access protocol, which would essentially transmit these packets from one place to another. And it doesn't do routing. So you're staying on, you're just transmitting from one computer to the other. Well, then there's the network, right? That does routing. So when you have an IP address, that would be the private IP address of a router, like my router, you would be able to find your way there on the local area network. And in fact, if you had an IP address that wasn't private, you could find your way there on the internet. And then comes the transport layer, and that goes on top of the internet protocol layer. So there you have transport control protocol, transmission control protocol, and then you have user datagram protocol, UDP. And then comes session layer. That's where you have your logins. Presentation layer, that's internet inter-orb protocol, which is a mechanism of passing objects from one place to the other using CORBA, which is Common Object Resource Broker Administration, or RMI, which is Remote Method Invocation, or DBNet, which is a way to communicate to relational database management system backends. So in other words, these are specialty protocols meant for special applications. And then on top of all of this, you could have a browser that uses HTTP or an email client or whatever you like. So everybody's got protocols for everything. And in fact, you can make up your own protocols, which of course doesn't necessarily make you friends, but you can do what you want. It's a free country. So typically in the physical layer, we already talked about wires and, oh yeah, wires, right, wires. So Ethernet, that's wire-based. That's a baseband communication mechanism. And you can go at many gigabits per second. And of course, 100 gigabit per second is typical. I'm up at 100 gigabits per second now. Internally, actually, I'm mostly 1 gigabit per second. And then data link layer. This is where you have Ethernet frames and the so-called media access control sublayer, or MAC address. And that is where you have access to the so-called hardware address. Typically, every piece of hardware will have a unique MAC address. And that goes into a something like a network appliance. It could be an Ethernet card or an Ethernet chip. And you would have that for Wi-Fi as well. And for routers, things like this. There's a thing called a top-level domain, .edu, .com, .gov. Every country has its own top-level domain. I think there's 400 and a fraction countries. So if you want your own top-level domain, just go to the United Nations and say, oh, look, I bought this island and it's a country and I need a top-level domain. I could call it .dl for Doug Lyon. And everybody could say, hey, welcome to Doug Lyon country. Wouldn't that be fun? We could have our own laws too, which means, I guess, I would never have to break the law because I could make the law. And so if you're in Windows, this is kind of an old Windows operating system reference over in here. You could see how the location of the hosts file kept changing as they went from one Windows operating system to another. I think this is the common one that you use now. System 32 drivers, etc hosts. You can check me on that. I'm not on a Windows system, so I can't check. etc hosts, that's where Unix and the Mac would store their list of hosts. And you can kind of see that in my system here. Here, I'll just show you real quick. So here's a list of hosts. So I've got my little Raspberry Pi, an Orange Pi, my Mac Mini, a MacBook, personal supercomputer, an Air, a TCP/IP bridge to an RS-232 interface, cameras, all these different laser printers, varieties of different wonderful things, all with IP addresses. And presumably you can ping these things. So for example, if you wanted to, you could ping Mini, or you could ping by IP address, ping or ping Mini. And mapping from Mini to the IP address is done in the hosts file. So the local machine is providing a domain name service mapping. Now comes this idea of socket programming. Now, to get to a machine, you certainly would like to have the TCP/IP or UDP/IP address, but then you also need the port, because the services will all be listening at a specific port. And when you connect to the machine, you're going to want the port. And then, port 80, for example, might be something like HTTPD, which is the Hypertext Transfer Protocol daemon, or web server. So if you went to services to look for ports, and you went up to port 80, there it is. So there's your Hypertext Transfer Protocol daemon, and he's also available under User Datagram Protocol. So that's a way in which you connect to the local area network, to the service provided on the machine through the local area network. If I could to ping, let's say www.fairfield.edu, probably get to it. And if I said telnet to www.fairfield.edu using port 80, I could say get, and it returns a little bit of HTML. And so you can see that with Telnet on port 80, I basically go in and tell the server, hi, I'm a browser and I'm doing get without a particular file name. And then it just says, hey, you don't know how to use get, and gives me back some HTML. So that's cool. I could probably render that if I wanted to, but why bother? It doesn't look particularly interesting. So every service has its own port, and you connect to it directly, creating a stream, and then you issue a protocol like get, and then it comes back with an answer. So socket programming allows you to use an IP address and a port to gain access to services. And you can use it for the web, you can use it for distributed computing, concurrent computing, network computing, virtual connections, internet interoperability protocol, remote method invocation, all of that goes on top of that layer, the TCP IP layer. So that's your network layer. And when I do a ping, I'm using port 7. Time is port 13. All kinds of interesting and wonderful services. And here's a example program where I create a server socket. So now I'm creating my own service on port number 1234, made up the port name, knew it wasn't going to be used for anything. So I registered the service, and now I sit there with a socket accept. That's a stop and wait protocol. I'm waiting for somebody to connect to me. Once they connect to me, this returns. The left-hand side comes back with a socket. I get an output stream from the socket, and then that output stream allows me to write responses. I can get an input stream from the socket, but I didn't do that here. I just wanted to get the output stream, and I put out, hi there. And then I close the connection, and that's it, and I'm done. So I've got a mechanism now to print out hi there to anybody who wants to connect to me. It's not particularly interesting, but they're going to need a client. So here comes the client. The client says, oh, I got to know your IP address, and I got to know what port you're on. We already know from server socket that we're on port 1234. We know our IP address, but the client has to know it too. So it's been hard coded in. And now we're going to get the input stream, and then we're going to print out, hi there, from, this is the hello world of network programming. So we'll go from the data input stream, get a string, print out hi there, and then close everything up. So that's server socket programming. That's the whole thing. And you could get as complicated with that as you like. And so that is using so-called unicast, which is a one-to-one protocol. If you want to go and do multicast, you can do one-to-many. And multicast is very good if you want to use UDP and broadcast something like your availability to any, for example, lookup server that wants to see if you're around. So if you're a printer and you want to find out if there's any print servers around that need to know that you're available now, you can use multicast to say, hey, anybody out there that's a print server? And then they can get a response back using unicast protocol that says, yeah, I'm a print server. What do you want? You can say, well, I'm a printer, and people can print to me. And so then you get listed in the network neighborhood as a printer that's available. So multicast enables a protocol with relatively minimal administration capabilities. So you can just go in and just say, hey, here I am, and is there anybody out there? Same thing for sort of using DHCP or Dynamic Host Control Protocol. You can go out there and say, hey, I need an IP address, and the router will respond specifically to you saying, okay, here's one, and it's available to you for only a specific amount of time. They lease it to you. And that's typical if you're on a Wi-Fi network with like a cell phone. You basically broadcast your existence to the DHCP server, and then the Dynamic Host Control Protocol responds to you with an IP address, and then you can conduct networking. There's a class called the INET address, and this is too much detail by half unless you want to get into internet programming. So that's about all I wanted to go through. Now that you've had sort of like a little taste of what it's like to create a socket, create a socket service, connect to it. After that, there's a lot of detail involved, and there's a whole course in network programming that you guys can take if you want to. So that's an interesting thing, and it allows you to gain insight into grid computing, cluster computing, and cloud computing, because this kind of network computing is so important and so fundamental to the shift in computer architectures. I felt it was important for you guys to sort of see it and try and, just get a basic understanding of what's going on. So was that all right? My quick overview. I know there's a lot more slides going on in here, but if I take you through them, I think you'll become a crowd of angry peasants carrying torches. You won't like it. So that's it for the PowerPoint death march. So now if we start to talk about layers and we say which layer provides a user interface, you can kind of see, well, there's a presentation layer, and that can give us an interface, but not necessarily a user interface, right? So that might be HTTP, Hypertext Transfer Protocol, but it's not where the HTML gets rendered. If we want that, we have to go into the application layer. So you can kind of see where the different layers have different roles. So last time, in our last exciting computer systems architecture class, we were on question number 18, I think. Is that right? Anybody remember where we left off?
Yes, it was question 18.
Okay, thank you. So here's question 18. Now we've got our little overview of threading. Given the following code, T equals new thread, T is now ready to run. Does that seem true?
False.
That's false, right? Because you have to pass something that's runnable into the argument on the thread, right? So if you don't have something runnable going in there, or if you don't subclass thread, that is not going to run. It won't even be ready to run. It won't compile. How many nested reference data types are there? Well, that's, one of those things you probably got when you were in the CS131 class, because you would have had, nested interfaces, nested classes, anonymous inner classes, anonymous, named inner classes. Then, by the time you're done, there'll be about 5 nested reference data types. And so if you, I don't know if you guys got anywhere with the CS131 class, did they cover that stuff in CS131? Nested reference data types. What is a nested reference data type? Have you never seen a nested reference data type? I'm reluctant to fire up my Java programs and show you one. But what it is, it's a class inside of a class, or an interface inside of a class, or an interface inside of an interface. And so you can have static classes or dynamic classes inside of other classes. And by the time you're done, you'll have 5. Trust me on this. Let's see. A member inner class is a nested class defined within a method. True or false? You guys really didn't take this stuff, did you? I often wonder how far along you guys get when you take that CS131 course. The answer on this one is false. The member inner class is just a class inside of a class, not a class inside of a method. So it becomes a member of the outer class. That's the That's the correct answer on this. So what is multi-threading? I think we kind of covered this. Is it a process in which many different processes are able to access the same information? It's no. Is it a process in which two different processes run simultaneously? No, that's not that, because in software multi-threading, certainly they take their turn. Is it a process in which a single process can access information from many sources? No, it has nothing to do with accessing information. It has more than one thread in a single task, is the answer. What is the name of the method used to start a thread's execution? You guys tell me.
Start.
Start. Thank you. That is correct. Thank you. Garbage collector is not a daemon thread. Now that one's, you might not know that. And the answer is false. It is a daemon thread. That means it dies when the main method dies, unless you want to invoke it so that it can run. You can change it from being not a daemon thread to being a daemon thread, so it keeps going, but it cannot prevent a Java virtual machine from exiting when all the other threads are finished with their execution, because it's not normally a daemon thread. So when the main dies, the Java virtual machine can terminate. Otherwise, if it found a daemon thread that was running, it wouldn't terminate, and then you'd have to wait for the garbage collector to be finished before you could quit. It's also a lowest priority thread, the garbage collector. And the reason why is you only want it to have it wake up when there's an urgent need or when it just has a little time in the background. Where does that leave us? Question 24. Synchronized methods have a cost in runtime, CPU time, memory, compiling, all of the above. So it's both CPU time and memory, right? When something is synchronized, it has to be executed atomically. It's going to make things cost in both CPU time and memory. And that's because it has to allocate a little space for the method to exist in the address space. Let's see what else. Question 25. Yield. Why would you invoke yield inside of a run method? So I'm running this thread, and all of a sudden, out of, I don't know, the goodness of my heart, I decide to invoke yield. Why would I do that? And the answer is if you're a thread programmer, you have to be a good neighbor. You're sharing resources, right? So the thread scheduler may not stop. It may just run you and nothing else. So if you want other things to run occasionally, you invoke yield, wait for some of the other threads to run, and then you'll get invoked again later. So invoking yield is a perfectly valid thing to be doing. It makes you into a good neighbor and not sort of a resource hog with one thread. So we talked a little bit about daemon threads. This is a task or a thread that remains idle until an event occurs. So it can keep going until whenever. Let's look at some more. Which three methods of the object? Which are three methods of the object class? So there's a class, you probably learned about this in CS 131, called the java.lang.object class, which is part of every virtual machine. And that java.lang.object class has to have some methods associated with it. You guys have any idea what they might be? Well, could it be is interrupted? Does that sound like a reasonable method?
Is it the middle one?
Well, let's see. Synchronized and interrupt are both available. Notify is not available. Notify all is. So is interrupted is not. It's the top one. I think you can find out.
Is there another one below?
Oh, there it is. Notify all and wait. There it is. Okay. That's the one you want. I think the easiest thing to do would be to look at the java.lang.object. Oh, stop it. So in principle, if you click on this and type Control B, now you can see every class is subclassed from the object class. Not a very nicely named class, I think. And you can see what's in there. So there's toString. Here's notify. Here's notify all. I think you're going to find, yep, here's wait. That's in there. And there's wait is overloaded. What else is in there? Finalize. That's so that you can have the instance harvested by the garbage collector. So there is a wait. That's what you want. Let's see. Here's computable object. Now that sounds like a good thing. And what it does is it returns something that's serializable. Something that's serializable means you can take an instance of it and convert it into an array of bytes, which means you can take whatever it is that it returns and pass it through a socket. That's so important because if you're going to have something computed on a foreign machine, you would like the answer to be returned to you. So what you do is you take the computable object and you invoke it remotely. And then you can pass the computable object over to something that invokes compute remotely, and it creates an answer, which is called a serializable instance, and takes that answer and pumps it back to the caller. And that way you can have a truly parallel computing environment. So this is a generic way to create computable objects. The objects are serializable because they can be passed across the network, and they return answers which are serializable, so they too can be passed back. So when a computable object instance is passed, what you get returned is something that's serializable, and it is an unformatted sequence of bytes. That seems true. Although if you know what it is, it's probably formatted, you just don't know what the formatting is. So that's, you know, is it unformatted? I guess you don't know the formatting, not from this, but presumably if you're making a computation and you know it's coming back with an image, it's an image format. So I guess it is formatted. Let's see. It's a means of returning something that is of serializable type. That has to be true. We know it's not of unknown type because we know it's serializable because of this. A means of computing something that can be returned as a computable object. No, it's returning something which is serializable. We don't know if it's a computable object or not. It's some answer. So you could say compute and it could come back with an image. So this is what you might call a framework, a distributed computing framework. So here comes a nice code example. And here's the server socket we saw from before. And here's the socket, which presumably is going to be returned when somebody makes a connection to our service. And this implements runnable, which means an instance of it can be passed into a thread. And it looks like it's got a port, so it's going to be listening. It'll accept connections on port 8000. And so here comes the new Lion server, the auto server Lion, which is this class, implementing runnable, passed into this thread. We'll start the thread, and so that starts our service. And then we go to sleep for a second. And here comes a run method. And what does it do? It listens on port 8000. And when somebody connects, the left-hand side of the SS accept will return, and we'll get an instance of a socket. But prior to stopping and waiting for somebody to connect, we're going to print out auto server thread waiting. And when the connection occurs, we'll make a new auto server thread out of this socket, and we'll hit start. And apparently auto server thread is an overloaded constructor, which can take a socket. So somewhere in here, we would see an auto server thread constructor, which takes a socket. Once the socket comes in, after the accept method is returned, we go and get the output stream and convert it into an object output stream, which means we're going to take the serializable instance and start reading in objects. Those will be our answers. And then we might even communicate to it using the object output stream. So here comes object input stream, object output stream. Sockets are bidirectional. You can communicate in both ways with the socket. And now it looks like we're going to read some objects. And if they're byte containers, we're going to get some kind of a thing. And we'll say if it's an instance of a computable object, that's great. And if it's not, then it's a bad object. And looks like computable objects are being passed back and forth in this example. And then we are going to do some kind of computation. So apparently we're the compute server. People are passing us computable objects. When they come in, we invoke the computation. The answer comes back as an instance of an object, but we happen to know that that's serializable. And so we're going to take that answer and we're going to write the object to the object output stream. So as a compute server, right, this is from the compute server's point of view, we're waiting for something to compute. Somebody passes in a compute job, we compute it, we grab an answer, take the answer, and write the answer back out. Now, how long does it take to do compute? The answer is, I have no idea. It could take 2 seconds, it could take 2 days, it could take 2 years, I don't know. The implementation is an implementation of something that just calls compute. So that could do anything. Who knows? Computes 10 bazillion digits in pi. I don't know what it does. Computes a frame out of a Disney movie. I have no idea. So this is an interesting point. This is just an accessor, which allows me to get the output stream external to the auto server thread. That's a terrible name. But there it is. So what are we computing when we invoke the compute method? Any idea? What is it doing? Are we computing a bytecode container? I don't think so. Are we computing streams? I don't know. We're not computing streams. Are we creating a serializable instance? There's no way for us to know, is the bottom line. The compute method could be implemented any way we like. So that's the bottom line on that one. Is DDR3 the fastest DDR RAM you can buy? I think we've already encountered the latest and greatest NVIDIA cards, right? They had something in there. And it wasn't it DDR4 just in the NVIDIA cards? These are like, I don't know, $5,000 cards or something bizarre. But yes, you can get faster than DDR3 now. DDR3, 800 million transactions per second. DDR4, I think it gives you a 12 nanosecond latency, which is basically the same, but gives you 21 gigabytes per second of bandwidth compared to the 12 gigabytes per second for DDR3. So DDR4 is about twice the bandwidth of DDR3, interestingly enough. So the answer to this is false, right? Because I can buy DDR4. I don't think I can buy DDR5. If DDR5 is available, has anybody here bought any? Do they even have DDR5? You guys can tell me. Whatever happened to DDR? Is there DDR5? Yes. And it was released on July 14th, 2020. How about that? So this is apparently my skill set is going obsolete. July 14th. That's recent, right? So probably it says Rambus announced DDR5 in September 2000, but they didn't ship it until that's released 2020. So I don't know. Maybe somebody uses it in some computer somewhere. I don't know. I'll bet you'll find it in the latest $10,000 NVIDIA graphics card. Somebody out there is going to want to use it. And presumably it'll be terribly expensive. So that gives us a little bit of insight into homework 7. We had a little bit of a review with the network programming. And what I wanted to do was kind of give you a little bit of insight into a computer architecture that you may encounter if you ever take the microprocessors class. This is a block diagram of a Mega 32U, also known as the Arduino Uno. And first thing I would point out is that it's got memory for double EEPROM, it's got memory for flash, and it's got memory for static RAM. The memory for the double EEPROM is interesting because even if you load a brand new program into the CPU, that memory will not be erased, not unless you specifically overwrite it. When you do load a new program in, it goes here into flash, and there's like 32K of flash on this little chip. And if you want to figure out why this is a Harvard architecture, it's precisely because it has its memory for programs separated from memory for data, which is the static RAM. So one thing you can say about this is it's a Harvard architecture because this little finite state machine called the AVR CPU, by the way, everything inside of this dotted line, that's on the chip. So anything that comes out of the dotted line, these are wires that you can actually physically wire to in order to be able to connect to this to the chip. And what we see in here, because we're dealing with flash memory that contains our program, is known as the Harvard architecture. So that right there stores all your program. That's Harvard architecture right there. And so the block diagram is interesting because it allows us to avoid too much detail. Here's like some A to D converters. They are memory mapped into the data bus. So their data can be accessed by using addresses. It's got some timers and counters, analog comparators, and interesting buses. Here's an SPI bus. Here's a 2-wire bus. And it's got a bunch of interesting timers and such. So when we think about, computer architecture, you think, why did they put all of this into this one chip? And did they really need to do that? And the answer is no. Initially, you didn't find anything like having 3 kinds of RAM inside of a chip. People couldn't, they didn't have the transistor budget for that. So initially, these kinds of things weren't available. And in fact, you can see that in some of the older architectures. And we might have just enough time to take a look at one. Let's see. See if I can get it in here. It's going to be under history. There it is. So what you can see, if you wanted to look at what Intel came out with, initially it was called the Intel 4004. And you can see that in here. So this is $60 for this little chip, 1971, which would be $387 in 2020. Ran at 700 kilohertz, contained 2,300 transistors. The first one, I guess, came out at 100 kilohertz, very slow. This is what it had. This is it. No RAM, no double EEPROM, no flash memory. All of that stuff was external. And this is a 4-bit machine and only had a 4-bit internal data bus. And that's it. In comparison, you can now get for $1.10 one of these little AT-Tinies. That's like a little 50-cent chip down in there. And that's about 700 times cheaper. And it's got 8 megahertz processor and 32K of flash memory all on the chip. And when you look at the AT-Tiny, which is what that is, that's the 50-cent chip, you can see he's got the static RAM, the double EEPROM, he's got flash memory, he's running 8 times, more than 8 times faster. If it's 8 megahertz versus 100 kilohertz, it's many times faster. And so that's an interesting point. And here's the program counter going into the flash memory. So you can see the program counter does not go into the RAM. The static RAM is just used for addressing and storing data. The program counter is used to get to the next instruction in the flash program memory. So this is a true Harvard architecture right in through here. And so that gives you a little insight into that. When I first got started in computing, we were using the 6502. This is 6501. And 6502s were $70, 1975. And they had an architecture that was also devoid of any RAM, really just registers. That's it. And this is the kind of computer you could get back then. Not a particularly interesting computer. This is a picture of the computer that I have in my attic. I just looked it up on eBay. Apparently somebody wants $10,000 for it, which is crazy. But yeah, it's got the little 6502, and that's 1K by 8 of RAM and 8 2102s sitting on the side. And that's personal computing when it first started. And you stored your program on a cassette deck. Crazy, right? So there you have it. A little background. We're kind of spoiled now because we get our little Arduino Unos for almost nothing. And it's a matter but then $10,000 for this. Nobody will buy that, I'm sure. So anyway, there you have it. We've gotten our homework 7 done. It's due at the end of the day on Thursday. And next Thursday, we're going to start covering the midterm. So stay safe, and thanks a bunch for your attentions.
Thank you.